if what we want is an invariant for rational tangles, let's think about ways of representing elements in this group, so combinations of operations on tangles, using other kinds of mathematical objects. So the first thing that I thought about was I was trying to work through this today is what if we just think about what these operations are doing, not to the whole tangle, but just to the people standing around the vertices of the tangle. So let's say I label my people out here A, B, C, and D. And here's my tangle G here in the middle. What is T, my dance step T, what is T going to do to the order in which the people are standing around the vertices of this tangle?
It's going to switch B and C.
It's going to switch B and C. So C is going to end up here. B is going to end up down there. Here's A. Here's D. Okay. We have a way in abstract algebra, kind of a standard way, I guess, of representing the thing that happens when I have a set of 4 distinguished elements, A, B, C, and D, and I transpose the middle pair of them. What's a way that I can write, what's a notation that I could use to represent this permutation?
You do a set of, oh.
So one of the standard ways to do this in group theory is to use what we call cycle notation. Right? And in cycle notation, the way that we read this is that the thing in the second position ends up in the third position, and the thing in the third position, wrap around to the outside and back to the beginning, ends up in the second position. Right? So second thing goes to the third thing, and the third thing goes back to the second thing. So this is the transposition of the second and third elements. So if we're using that cycle notation, we would associate T. So T is an element of the group gamma of operations on tangles. We would associate with T the transposition 2, 3 in the symmetric group on 4 symbols. This is the permutation group on 4 symbols, right, from group theory. Okay, so that's what would happen to the people standing on the outsides of the tangle when we do the T step. What happens when we do the R step? So if I start with the same tangle over here in the beginning and I do R to it, my tangle in the middle is going to rotate, which we're not going to care about right now because we're only looking at the people standing on the outside. What do we end up with?
Do you change with A, change with
Yeah, you got it, exactly. 1, 2, 3, 4. So the person in the first position ends up in the second position. The person in the second position ends up in the third position. The person in the third position ends up in the fourth position. And the fourth position ends up in the first position. So we call that a 4-cycle or a cyclic permutation. Oops. D, A, B, C. And so to the tangle operation R, we can associate the element 1, 2, 3, 4, the 4-cycle 1, 2, 3, 4 in the cycle notation on the permutation group of 4 symbols. So what this does is it gives us what actually mathematically we would call a representation of this tangle group using elements of the permutation group on 4 symbols. So that seems like it's kind of nice because we have a lot of, if you took group theory last semester, you probably spent a lot of time looking at permutations and how to compose permutations, how to simplify combinations of permutations, and so forth. Because it ought to be true that the same relations which hold for the tangle group up here should also be satisfied by the images of those tangle generators inside of S4. Let's verify let's verify whether or not that's true. Just clear off some space here. Let's suppose that we did TR. Let's just try and write down what TR would actually look like in the symmetric group. So it would be the composition of 2, 3 with 1, 2, 3, 4. All right, so in other words, if I did T first, then I'd be trading 2 with 3. So 2 would go to 3, and 3 would go to 2. Then if I do this, the thing in the first position would go to the second position. The second to third, third to fourth, fourth to first. Maybe just to avoid screwing something up, I'm going to write this like this. So my T is going to switch those middle two positions and give me a C, B, D. And then my R is going to move everything to the right one, with D moving all the way back to the beginning. And I'm going to end up with D, A, C, B. So what would that be in cycle notation? All in all, 1 would go to 2, 2 would go to 4, 4 would go to 1, and 1 goes to 2. Wait a minute. Yes, right, because notice C is actually staying put. And so 3 stays in its place, and we end up with a cycle, 3 cycle. 1, 4, 1, 2, 4. Yeah, there we go. For some reason, I always trip over cycle composition. Like if you look at my abstract algebra video stream from a few years ago, there are some early videos in that semester where I just totally make a mess composing cycles. Yeah. So what I'm looking at is the starting point to the ending point comparison. Right? We did T followed by R, right? And I wanted to know what in total has happened. So let me trace the fate of each of these symbols. So A in my first position ends up in the second position. So that's where the 1, 2 comes from. And then I want to know, where did my thing that was in the second position end up? So where did B end up? B ended up in the fourth position. So that's 2, 4. And then looking back in the beginning again, what happened to my thing that was in the fourth position? D. It ended up in the first position. 4 wraps around back to 1.
Okay. Right. So we don't really care about C because it stayed in the same.
Yeah, if we wanted to be really fancy, we would just write a 1 cycle here, 3.
Okay.
Right? But a 1 cycle doesn't actually do anything to permute the elements, and so it's the same as the identity. So usually we just conceal it. Right? And so when we compose these two things together, we end up with a 3 cycle. And what is the order of a 3 cycle? How many times do we have to apply the same 3 cycle before we get back to the identity? Yeah, 3 times. 1's going to go to 2, which is going to go to 4. Yeah, it's almost... Yeah.
Okay.
1 goes to 2, 2 to 4, 4 back to 1, and then we're home. Same thing with 2, same thing with 4. So just a single n cycle by itself in the permutation group has order n. Right? And so TR to the third power is going to give me the identity. So TR to the third power was the identity in gamma, and it maps to this thing, 1, 2, 4, which when I do that 3 times, also gives me the identity in my symmetric group. Right. So what's happening to the vertices when I look into this relation is also being satisfied. So when the tangle, maybe another way to say it is when the tangle undoes itself by doing TR 3 times, the vertices also, the people on the vertices end up in the same spot that they started with at the beginning. So that seems nice. What about the other relation, R squared? So if I do R squared in the tangle group, I get back to the identity. But what about if I do R squared in the symmetric group, the 4 cycle 1, 2, 3, 4, twice? We don't get back to the identity. Why not?
We need to go around 4 times.
Yeah, we would actually need to go around 4 times. So notice this is a difference here, that R is a 90-degree rotation of my tangle. And if I rotate a tangle by 180 degrees, I still have the same tangle. Same. But if I repeat the 4 cycle twice, let's do the quick carousel notation on that one. So if I move everything over to the right one, and then we move D back to the beginning, we're going to have DABC. I do it a second time. I'm going to get AB on this side, CD on this side. And so if I want cycle notation, I'm going to note that A in the first position ends up in the third. The third ends up in the first. So I actually get a 1-3 transposition. The C and the A are just trading places. And likewise, the B and the D are trading places. But notably, I do not get the identity, right? And that's because even though the tangle is the same, the people at the vertices of the tangle are in different places after we've done R twice. So not the same permutation. And so the lesson here is that if we're looking for a faithful way, an invariant, right? If we're looking for something that can adequately represent exactly what's going on with these tangle operations, it's not enough for us to just look at what's happening out on the 4 vertices, right? It's not enough for us to just use the symmetric group on 4 symbols as a way to understand what this group is. It's kind of a shadow of what's going on. It's not capturing all of the interesting behavior, because somehow the fact that R squared is the identity when R squared is not the identity over here means that there's more to the story, right? That it's not enough just to look at what's happening with the vertices at the ends of the tangle. We need something that has a little bit more structure in order to get to where we're going. Using the symmetric group on 4 symbols kind of gave us a part of the story for how we might think about what this tangle group is, but it wasn't enough. We'd like to have something that actually has more structure. The symmetric group on 4 symbols, all we can really do is compose those permutations one with another. There's not a lot of arithmetic, not a lot of algebra in the symmetric group, other than composition. And yeah, you can get a lot of mileage out of that. But ultimately what we want is we want to be able to represent this tangle group using something that has more operations available to us. And in particular, we call them rational tangles, because ultimately what we want is a rational number to be able to be our invariant for these tangles, to stand in for the identity of these tangles. And so what we'd like is we'd like to be able to take T and to take R from my tangle group and represent each one of them by functions. I'm going to call them T of x and R of x, lowercase, to distinguish them from the elements inside of the tangle group. And that these should be functions that have as their domain the rational numbers and have as their codomain the rational numbers, right? So a function that takes a rational number and produces another rational number for us. And the minimum that we would like for these functions to do is that when I combine these functions with one another, they should satisfy the same relations that the tangle group elements did, right? So for example, we need for T, we know that T is a free generator. In other words, no matter how many times I compose it with itself, I get something which is still not the identity. Right? It's not the identity. And furthermore, as I get higher and higher powers of these T's, if I combine them together, I also need to know that if I have, let's say, K powers of T and I compose them with L powers of T, that what do I need to get here? So I have K powers of T over there, and I have L powers of T over here.
T to the K plus L.
Yeah, I really just need to get K plus L. And that needs to be true of the function little t of x that we're using for this as well, right? So we need to have this nice property be satisfied by this function that we're getting. We need this nice additivity. That if I do this thing k times and then I do it L more times, that it's the same as if I just did it k plus L times to begin with. So can we think of something that we can do to rational numbers that has that freedom, right? That every time we do it, it gets us a new answer. And that if I do it k times and then L times, that I've done it a total of k plus L times. So what might be an example that we can use just to get ourselves off the ground? A function that, given any rational number, is always going to give me a new rational number in a nice progression. So let's think of this function as the function that just adds 1 to the rational number that we give it, right? So we can check, and we should check, right, that every time if I do it twice, let's check and see what t squared actually does. So t squared of x, that's, in other words, saying it would correspond to t of x. So that's t of x plus 1. That's x plus 1 plus 1. It's x plus 2. So it's not the identity function, right? If I do t twice, it's the same as adding 2. If I do t 3 times, it's the same as adding be really brutal and write all this out if we want to. But let's skip a step. This is going to be t composed with t squared, and we know t squared of x is x plus 2. And t of x plus 2 is going to be x plus 2 plus 1. It's x plus 3, which is not, again, the identity function, right? So it would seem that no matter how many times I compose t with itself, I'm never going to get back to the identity. Right? In fact, we can come up with a formula for t to the n. So we know we want this to correspond to t composed with itself n times of x. And we suspect that that's going to be, what's the formula going to be? X plus n. That seems like something that we could prove. Right? We could prove by induction that this formula actually, that this actually is a closed form for what we get when we compose t with itself n times. Maybe we'll do an induction proof in a minute if we have interest to do so. But for now, let's just observe that the pattern that began in these couple of examples seems like it will continue. Right? And no matter what, unless n is, what's the only value of n here that's going to make t to the n power the identity function? The function which does nothing. Yeah, the only way to get the identity function is if n is equal to 0. So this would seem to satisfy that freedom property for the generator t, right? That no power of t except for the 0th power is going to give me the identity back. Cool. So if we decide that that's what our t is, now the really interesting part is how do we satisfy this other relation? This one was the one that was really interesting for us today, right? How do we figure out what function on the rational numbers we can make this r be that will cause this to happen? And which will also do this. It also will satisfy r squared as the identity. So we're looking for a function which is its own inverse. Maybe that should be where we start searching. Let me clear out some space here. Let's think of some examples of functions from algebra which are their own inverses. So r composed with r is the identity. In other words, r of x has to equal x for all x. What are some ways to think about this question? Maybe even using the rule of 4. Let's think about the graphs. The graph of r of x for a second. What's the relationship between the graph of a function and the graph of its inverse function?
They're symmetric
About the line.
About
the line of x equals x. Right. So whatever this r is, yeah. So this is hooking back into stuff that you all teach on a regular basis. There you go. So whatever the graph of r of x is, the graph needs to be symmetric about the line y equals x, right? So that the function can be its own inverse. And that limits the universe pretty substantially to what the graphs can look like. What are some examples of graphs that are symmetric about the line y equals x?
X cubed. X.
X. So x itself, right? R of x equals x. And why do we not want that as our example here? Because it's already just the identity, right? It's trivial. And we know that R is actually a meaningful operation on tangles, and so we want its representation here to also be not the identity. So R of x equals x fits this description, but other stuff might too. What's another example?
Negative x.
Negative x. So there's a candidate. That's a graph that's symmetric about the axis, and that's a non-trivial function. So let's have that as one of our possibilities. Can you think of others?
X cubed.
X cubed. Let's try it. So here's that graph. But I don't think that graph is, it's an odd function in the sense that it's symmetric about the origin, but the graph's not symmetric about y equals x. If I mirror it over the line y equals x, I'm going to end up with this thing right here, the cube root function, right? So cubing something does not undo itself. That's what we're really talking about here, functions that undo themselves when you do it twice. So taking the opposite of an opposite gives you back the original number. So that function is its own inverse. By the way, functions which do this, because I like vocabulary words, are called involutory. Or we call an R an involution. So functions. But the square root of something doesn't give us back the original
1
number.
over x.
1 over x, reciprocal, that seems like it will do. Because what's the graph of reciprocal look like? Right?
Yeah.
R of x equals 1 over x. If I take the reciprocal of a number, I get back to the original number. So that seems like it fits. So opposites work, reciprocals work. I'm trying to think if we can come up with other examples. I think if we try to come up with any other examples, we either need to introduce functions which are not strictly algebraic, like we might need to introduce transcendental functions like logs, exponentials, that kind of stuff. Or we could think of other examples that maybe are just combinations of these. Right? So 1 over x is symmetric about the line y equals x, but what if instead of these hyperbolas being in the first and the fourth first and third, what if I had them in the second and the fourth? So here and there, that's also still symmetric about the line. Yeah. So the opposite function is an involution. The reciprocal is an involution. If I compose them together, the opposite reciprocal is also an involution. So here are 3 candidates for what we might have. Maybe we can play around with these and see if we can make some sense out of it. So to figure out which one of these we want, I think what we need to do is return to some of the tangles that we started out with today and figure out if, for example, so if we can make TR cubed equal to the identity. So TR cubed of x needs to equal x for all x. So let's just figure out what TR is for each of these examples. So if R of x is minus x, and I do TR, in other words, that's first apply T and then apply R. So we run into a little bit of notational irritation here when it comes to using function notation. So I want to be really careful. TR cubed of x means take x and then first apply T to it and then apply R to it and then apply T again. So now I can see that there's kind of a limitation to how function notation works, that where we read these compositions from left to right, when we start using actual function notation, we tend to read it from right to left. So that's something that every algebra teacher at just about every level has to sweat this irritating detail at some point. Because, for example, in linear algebra, when we write matrix multiplication, we also read matrix multiplication from right to left to right, rather. But the linear transformations that they represent, because we write functions operating on the left of variables, accrues from right to left. So that's just something to be careful about. So when I think about the question about what is TR, TR of x is apply T first and then apply R. So maybe I'll kind of just make some room over here. I'm going to have you work on these composition formulas in a second. So TR of x is R applied to T of x. And so the task for you for the next few minutes, and maybe I'll get you into, well, we have 3 examples. Yeah, all right. 3 examples and 4 of you, so maybe 2 of you who want to work together, is come up with a formula for R of T of x. And then come up with a formula for what happens when you apply it 3 times. So what's the formula for TR? And then what's the formula for TR to the third power? Because ultimately what we'd like is we'd like to find the one of these, if there is one of these three, for which TR applied 3 times actually gives us the identity function back. So we had these 3 different candidates for, we decided that each of these 3 functions are functions on the rational numbers, first of all, right? So each one of them is going to take a rational number for input and give us a rational number as output. And each one is an involution. Each one of them is its own inverse. So these are our 3 candidates possibilities for what can represent the R function as an operation on the rationals. So we're just going to test to see which of these, if any, satisfy our most complicated relation that we have to worry about, the TR quantity cubed equals identity. So starting with just R of x equals minus x, the opposite function. John, you found out that TR, the composition of TRx, so R of T of x, has the equation minus x minus 1. And then using that as a function, if we compose that with itself 3 times, what we actually find is that when we just do it twice, what happens?
When we do it twice, we end back up at x.
We end back up at x, minus x minus 1, minus 1. Distribute the minus through, this becomes x plus 1 minus 1 equals x. So TR squared in this example is already the identity, which doesn't bode well for this being a good representative for us, because that also means that TR cubed is the same thing as TR.
Yep.
Notably, TR cubed is not the identity, because TR squared was already the identity, and TR was not. So, okay, so opposite function doesn't seem to work. How about the reciprocal function? So, Sam, when you computed TR in this example,
1 over x plus 1.
1 over x plus 1. Because first thing you do is you hit this with t, and so it adds 1, and then take the reciprocal. So x plus 1 reciprocal. Whoops. I screwed that. What did I screw up here?
It's TR squared.
That was, yeah, so what I just wrote here is actually TR squared. My fault. Just put a squared there. And then compose that one more time with TR to find out how that works. I wrote all this out of order. TR of x is minus 1 over x. There we go. There, I fixed it. All right. So then to find out what TR cubed is, we just compose this with itself 3 times. So TR squared is 1 over that thing plus 1, which my favorite way to simplify that is to treat it like a compound fraction. Just multiply the top and the bottom of the big fraction by x plus 1. Clears out this denominator, turns this into an x plus 1. So 1 plus x plus 1, x plus 2. And then on top, multiply by x plus 1 to get that. And then hit that with TR one more time. So 1 over that thing plus 1. I get x plus 2 over 2x plus 3. So def doesn't seem like the identity, right? Although what's interesting is we could probably propose a pattern for that particular function. What would we get for TR to the power n, do you think?
X plus n minus 1
X plus n minus 1
over n minus 1 x plus n.
n minus 1 x plus n.
Yeah.
That would be interesting to try and prove by induction that that's actually a formula for the nth iterated power of TR. But notably, which of those n's, which n is going to give us the identity function? N equals, well, even n equals 1 is going to give me x upstairs, but it's going to give me, oh no, I guess, yeah, I guess n equals 1 somehow gives me the identity. That doesn't seem right somehow, because TR to the first power was 1 over x plus 1. So maybe this formula doesn't actually hold up for all values of n. It's, in fact, I mean, it does seem to hold for n equals 2, right? X plus 1 over x plus 2, and then this increases by, all of these increase by 1 as we go from one step to the next, but maybe something happens at TR to the 4th that makes the pattern not necessarily work. So I'm just going to put a question mark over that. But certainly, most importantly for us, the third power is not the identity function. So this involution doesn't look like it works. For minus 1 over x, the opposite reciprocal, TR to to the first power is minus 1 over x plus 1. What happens when you do that 3 times? We get back to the identity, so let's just look at the algebra there. If I do this the second time, I'm going to get minus 1 over x plus 1 plus 1. Simplify that out, multiply by x plus 1 top and bottom. I'm going to get that on top, minus 1 plus x plus 1 on the bottom. So I'm going to get minus x minus 1 over x. So that's tr squared. Is that what you had for tr squared?
TR squared, yes.
Tr squared. And then if I hit this with tr one more time, tr, I'm going to get minus 1 over that thing plus 1, minus x minus 1 over x. Multiply that through by x on the top and the bottom. We have minus x up here, minus x minus 1 plus x on the bottom. And yeah, negative x over negative 1, that gives me x. So lo and behold, that's actually what we were looking for out of this process, right? We were looking for an r that was able to satisfy tr to the third power is the identity function. And now we just found one. So let's celebrate that for a minute, that we have found an example of a way to represent the operation r, which is a rotation of my tangle by 90 degrees, right? We found a way to represent that using a function operating on the rational numbers such that the combination of this t and this r function satisfy the same relationships as functions on the rational numbers that the group elements of my tangle group satisfied when we were untangling ropes in the middle of the classroom. So this feels like an important step forward, right, toward trying to figure out how we can get rational numbers to represent rational tangles, right? The tangles that we worked with today that are built out of this operation t and this operation r. So what's the ultimate moral of the story, the jumping off point that we're going to have? So here's some questions that we want to pick up on for next time. First is, are there limitations to this representation? In other words, is it possible that this t and this r might not capture all possibilities? Is there something that we can do to tangles, for example? Is there something that we can do to tangles which cannot be captured by this t and this r? Or is it a perfect one-to-one correspondence? And so far, just the fact that our t and our r still satisfy both of these relations, unlike when we were working in the symmetric group and we got one of these to work but the other one didn't, right? This seems like it's more accurate to how the tangle operations fit together with one another. And if that's true, then what this should allow us to do, is to create an invariant, a numerical invariant. So we can use these functions to create an invariant for tangles, and all we would have to do is to decide what number to assign to the empty tangle. So this is an element of my tangle, well, it's I guess the identity element of my tangle group, right? And what is the identity function, maybe, is another way to think about the identity function. I of x equals x. It can be seen as just sort of the 0th power of this thing, right? And we said that the nth power was what we get by adding n, so the 0th power is what we get by adding 0. Right? And so if we want to create a number which is an invariant for tangles, maybe the way to start that process is to assign to the empty tangle the number 0. So if I call my empty tangle 0, then I can identify the number of any other tangle just by applying t to each of these. Sorry, I don't want to use t here. I want to use capital T, right? if I apply t, capital T, to this tangle, I'm going to get, this twisted up tangle. But then in this representation, I should get the same thing as if I apply the function t to the representative of the empty tangle, 0. And if t of x is 1 plus x, then t of 0 is just 1. So the idea here is how to find a rational number that stands in for my tangle is first understand how my tangle was built, what sequences of t's and r's made up my tangle, starting from empty. Right? And then apply that same sequence of t's and r's to the number, the rational number, which represented my empty tangle, 0. So I want to close by going back to the complex example that we did, the last one that we did using the ropes at the end of our demonstration. So then how we would do that is we would take this presentation of my tangle, starting from empty, right? So when we wrote down this sequence of t's and r's, what we really meant was start with an empty tangle and then apply all of these tangle operations to it, right? So we're starting in here with the empty tangle. And so then how we would represent this tangle as a rational number is we would do this sequence of t's and r's, t, 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 r, t, 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 to the number 0. Right? So what would that look like? We start with 0, and we apply the t operation to it, which increases it by 1. Then we apply t again, increases it by 1. Then we apply t again, increases by 1, increase by 1. So then we're up at 4. And we've taken care of this first 4 t's. Then r. What does r do? Opposite reciprocal. So we end up with negative 1/4 after that step. Then we hit this with t's again. And t 4 times, I'm going to skip the intermediate steps here, is just going to add 4 to this number. So we end up with 15/4. And the idea now is that if these two functions, r and t, operating on rational numbers, satisfy all the same properties that this capital T and capital R in my tangle group satisfy, then the path that led us from 0 to 15/4 here is exactly the same as the path that led us from the empty tangle to this tangle, which means that this number, 15/4, should tell us everything that we need to know about the tangle, which we obtain by doing this set of dance moves. So we're going to call this the tangle number for this fraction. And where we're going to jump off on Thursday is by looking more deeply into the properties of tangle numbers and figuring out if we can convince ourselves that having just the tangle number to go from, that we can figure out how to build that tangle, first of all, and how to untangle that tangle, second of all. Right? Can we do it just from this single rational number, 15/4 in this example? How do we go from this to this? Or even more interestingly maybe, how do we go from this to that long string of maneuvers we can use to undo a tangle? Because we can do a lot with rational numbers, and maybe this is a way to help us understand how to simplify these long words inside of our tangle group. Just to satisfy that question, let's check it out and make sure that if I start at 15/4 and I do this sequence of things, that we should end up back at 0, which is the empty tangle, right? So one step at a time. So r is opposite reciprocal, so that's going to leave me at negative 4/15, right? And then I apply t to it, which is going to add 1, so that's going to leave me at 11/15. Then r is opposite reciprocal again, negative 15/11. T twice is going to lead me to 7/11. Opposite reciprocal again. T twice, I'm going to add 14 to that numerator and give me 3/7. Whoops, move that back a spot. Opposite reciprocal again. T 3 times is going to add 9 to this numerator and leave me at 2/3. Opposite reciprocal is going to leave me to minus 3/2. T twice is going to add 4 to my numerator and leave me to 1/2. R, opposite reciprocal. Add 1. We get to 0. So it works. And so our job is to convince ourselves that that's not an accident, first of all. And then also to think about if somebody just randomly hands us a fraction, a rational number that represents a tangle, how do we know that there exists an algorithm which is always going to get us back to zero? Are there any fractions out there in the wild that wouldn't be able to be untangled through some process like this one? And if we pick a process, how do we know we've gotten the most efficient process? This one over here had, 16 or 18 steps? This one over here has 41, right? They both ostensibly get us back to zero. But can we be more systematic about it? Because now we've turned this question from a question about untangling tangles into a question about transforming rational numbers, transforming fractions, by either adding one to them or taking their opposite reciprocals. And is there a smart combination, an efficient combination of doing those steps that can get us from any rational number in the universe back to zero? If there is, then we can use that same process to tangle and untangle ropes in a way that's always going to give us the same tangle for a given rational number.